My name is Craig Lefkowitz, and I'm a developer advocate for AWS CloudFormation. Before joining the CloudFormation team, I worked as a consultant with AWS Professional Services, and I got to observe how many customers deploy their applications. I've seen everything from emailing copies of zip files to some really cool continuous deployment systems. Today, we'll be covering an overview of GitOps. I'll tell you a GitOps story. I'll talk about the terminology, such as what is infrastructure, declarative versus imperative, the source of truth, and drift. I'll also do a few demos along the way. So let's start with an overview of what GitOps is and what it can do. GitOps is a set of practices that brings a DevOps culture to tasks that usually fall under the responsibilities of IT operations. The term was originally coined by Alexis Richardson in 2017, and when he used it, it was in reference to managing Kubernetes-based applications. Because of this and other specific characteristics of Kubernetes, the term has largely been synonymous with Kubernetes. But there is nothing inherent to GitOps that requires Kubernetes for GitOps to be practiced. Today, we're going to discuss how application developers who aren't using Kubernetes, or who might be using Kubernetes, but they may also be managing infrastructure that's outside of a Kubernetes cluster, can leverage GitOps techniques. When a company moves to a DevOps culture, they build the processes, practices, and tools that are needed to continuously release new software. This is done by implementing continuous integration so that every commit is built and attempted to integrate into the main or feature branch of a product. Once they've achieved continuous integration, they can then work on continuous delivery. Continuous integration ensures that there's always a deployable version of the product ready for deployment. Continuous delivery is the collection of tools that attempt to automatically deploy updated versions of the application to various environments. These environments could be staging environments, they could be QA test environments, pre-production, or even production environments. Once the application is deployed, DevOps principles expect that there will be some kind of monitoring or observability tools in place in some or all of those environments. These monitoring tools allow application owners to understand how their application is performing so that they can identify and correct potential errors. Let's look at a simple scenario of a DevOps team at a small online retailer preparing for an upcoming holiday season. Someone has decided that the business should support an additional category in their catalog devoted specifically to holiday sales. An engineer is assigned to update the e-commerce application to support this additional category. They determine that the changes need to be made in several places, specifically the front end, so that they can apply a holiday theme to the web page, a back end, so they can process transactions, and an additional database to hold the holiday category. Our engineer files a ticket with IT operations to request a new database based on a rough estimate of the sales volume that they expect the application will need to support. Once the database is created and the ticket's closed out, our engineer will merge their changes and the application will be updated to support the new holiday category. But suppose that the engineer underestimated either the volume of the holiday traffic or how well the new database would handle a given volume of traffic. The application starts experiencing throughput and latency issues, and now the engineer faces a decision. Do they make another request to IT to provision a larger or maybe even a different database? Or do they attempt to update their code to be more performant? Or do they have time to do both? But what if they try and do both and only one is completed in time? These questions create risk to the business, and they're fundamentally connected to the development team relying on another team to make changes to the infrastructure that their application runs on. If this team were practicing GitOps, our engineer could update their infrastructure definition files and have a new, larger database available quickly. This agility would allow our engineer to test combinations of different database types with performance improvements to determine which approach best meets the team's needs. In this session, we'll explain how GitOps helps solve this problem and save the holiday season for the engineer in our story. As we saw in our previous example, the infrastructure, the database, was controlled by another team within the company. A request was made by our engineer to have a database created. This request was in the form of an IT ticket, but it could have just easily been done through an API. The operations team could have some kind of company-facing API such as create database that the engineers can use to provision a new database. From the perspective of the engineer, this database is infrastructure. However, from the perspective of the IT operations team, this database is application data. It's some resource that's created in their data plane as part of the regular API operations of their application. Because a resource can either be data or infrastructure, depending on your frame of reference, it's very important to have clear boundaries of ownership for each resource. Things like shared databases or resources that are owned by one team and managed by another are examples of unclear ownership boundaries, and these are what lead to the breakdowns that we saw in our example. One of the 4 tenets of GitOps, as outlined by Alexis, is that infrastructure definitions should be declarative as opposed to imperative. To clarify what this means, let's look at a television remote. If we wanted the volume set to medium and the channel set to 5, we would have to know where the volume is now and then tell the remote either lower volume or raise volume until the volume reaches the medium setting. Likewise for adjusting the channel. We would need to know which channel we're on now and then press increment channel or decrement channel until we arrived at the desired channel of 5. With a declarative remote, we would simply say volume medium and channel 5. This approach makes it easier for automated tools to reason about the system. It can see the desired state, channel 5, and query the system for the current state, say channel 7, and then apply the correct operations to transition the system safely to the desired state. We can see that this approach is better for an automated tool because you can give it a starting state and an ending state and let it decide how to make the transition. If we relied on an imperative description, we tell the tool, you're at state A, you need to get to state B, and here are the instructions you need to follow to get there. But if we don't ensure that the system is actually in state A when we start, we can't guarantee that the system will end up in state B when we're done. So I'm not entirely convinced that we need to make such a distinction as strongly as the GitOps tenets imply. While it's certainly important that there's a declarative definition of our infrastructure somewhere in the infrastructure provisioning workflow, it's not a requirement that the end users only use declarative infrastructure definitions to describe their infrastructure. We're seeing more and more investment in tooling that translates infrastructure definitions from imperative languages that developers are comfortable in, such as Python, TypeScript, Go or Java, to a declarative syntax that infrastructure provisioning engines require. This brings us to the next tenet of GitOps. There should be a single source of truth for the infrastructure definition. In Kubernetes, this would be something like a Helm chart that's stored in a Git repository. In a non-Kubernetes world, this could be a CloudFormation template or an AWS SAM application or a CDK application, all of which are stored in a Git repository. It's less important to focus on what kind of source of truth you want to use and more important to focus on where the source of truth is located. The reason the location is important is because you're going to direct most of your effort to ensuring that the source of truth has the right balance of security and accessibility. When an engineer wants to make a change to the infrastructure, they're going to check out the existing source of truth. They'll make some changes locally, then push those changes to a branch, and then they'll merge those changes back into the main branch. Then there's the continuous integration system that checks out the file, scans it, does some testing on it, and then stages it for deployment. Finally, the definition file is sent to CloudFormation, where the infrastructure is provisioned. There are many copies of the source of truth made throughout this workflow. Stages before the source of truth place a significantly higher premium on ease of access, while stages afterwards are more concerned with the security and integrity of the file. This means that the source of truth is where you need to carefully balance both accessibility and security. For most GitOps workloads, we'll use the main branch of the Git repository as the source of truth. We'll want to ensure that only pull requests that have been approved by the correct approvers are merged, and that the infrastructure definitions on the main branch are deployed quickly to eliminate any potential race conditions to merge conflicts. Now that we've established some common principles that are shared by both Kubernetes and non-Kubernetes GitOps practices, let's take a look at how customers can practice GitOps on AWS with Atlassian's Bitbucket and Bitbucket Pipelines. Bitbucket Pipelines is an integrated CI/CD service built into Bitbucket. It allows you to automatically build, test, and deploy your code based on a configuration file in your repository. AWS offers a fully managed infrastructure provisioning service called AWS CloudFormation. CloudFormation gives you an easy way to model a collection of related AWS and third-party resources, provision them quickly, and manage them throughout their lifecycle by treating infrastructure as code. A CloudFormation template describes your desired resources and their dependencies, so you can launch and configure them together as a single unit that we call a stack. CloudFormation allows you to perform a sort of dry run of the changes before they're applied, and this is called a change set. And it tells you all of the changes that will be applied if this infrastructure definition is deployed. This lists all the resources that will be created or deleted or modified that you'll see in the change set. Now, let's walk through a brief demo showing how this is done. I have a Cloud9 environment on the left and Bitbucket on the right. I'm going to clone this repository, so I copy the command and I paste it into my terminal. I then navigate into the local files on my computer, and then I'm going to open the template file. I currently have 2 buckets in there, and I'm going to add a third. I then save the file, and then I'm going to do a git add and a git commit. Now I'm going to do a git push so that my changes get pushed to Bitbucket. I then navigate to the pipelines console in Bitbucket, and I can see that my pipeline is running in response to the push I just did. When the pipeline is finished, it emits a URL that I can use to see the CloudFormation stack that was created. I put the URL in my browser and I navigate to the resources tab in the stack, and there's my third bucket. Clicking over to the resource, I can see the bucket in the console. Now that we've seen how we can automatically update our infrastructure, astute viewers may be asking themselves, Okay, but how is that any different than just opening the console and creating the resources by hand, or running a script to create those resources? And that's a great question, and it brings us to our next point, archaeology. Have you ever looked at an application and asked yourself, why is this here? Or why was this built this way? Of course you have. We all have. By using Git as the source of truth for our infrastructure definition, we can see the commit messages that are attached to each change so we can understand the reasoning behind each change. When we use Git on Bitbucket, we can also link the commits and pull requests to Jira issues so that we have a more complete understanding about why the change was requested. Using Bitbucket, we can also guarantee that the changes are reviewed and approved by other members of the team before they're deployed. So let's take a quick look at a demo that highlights this capability. In this demo, I'm going to again clone the repo and make some changes. So I copy the clone command and I paste it into my console. After it's finished cloning, I'm going to create a branch this time and make another change. This time I'm going to be adding a fourth bucket to my template file. I'll save the change and then do a git add and git commit. Finally, I will do a git push to push this new branch to origin, but of course I forget the syntax. Luckily, Git saves the day and provides me with the right command. I try it once more and success. I then go to Bitbucket to create a pull request to merge my changes into main. I add a delightful description, and here's where I would normally add reviewers to the pull request, but since this is a demo and I didn't have anyone to review my code, we'll just pretend that I did. I go ahead and click Create Pull Request. At this point, someone would review my code and approve it. I'm going to do this myself for the sake of the demo. Looks good to me. And then I go ahead and click Merge. Once the code is merged into main, the pipeline is going to execute, and the resources that I updated in the template will get deployed to CloudFormation. Here I'm going to grab that URL that takes me directly to the CloudFormation console. Navigate to my stack, check out the resources tab, and then I'm going to click on that new bucket that I created. I'm taken to the S3 console, and there's that new bucket. So let's talk about drift. Drift is described as the situation when the infrastructure definition file and reality are no longer in sync. This most frequently happens when someone makes a change to the system through the console, but it can also happen with a CLI or an SDK tool. Sometimes an overzealous compliance tool can identify a server as being unauthorized and very helpfully terminate the instance immediately. When these situations happen, we say that the stack has drifted, and we generally want to correct the drift in one of two ways. One way to correct it is to update the infrastructure definition to reflect this new reality. This is common when someone has created some additional resource manually and now wants it managed via the GitOps tools. The other way to correct this is to update reality to reflect the infrastructure definition. This is a preferred approach when the resource wasn't meant to be created or it isn't meant to be long-lived. And it's just easier to simply delete the resource than to attempt to import it into the infrastructure definition file. If you recall from earlier in the presentation, we discussed how one team's infrastructure resources can be another team's application resources. This distinction becomes much more significant when multiple teams have resources that they manage in a single AWS account. While we generally discourage this practice, the reality is that it's the only option for many teams because they may need to use a common VPC, or maybe they need to store objects all in the same bucket. For example, a Cloud Center of Excellence team may own an S3 bucket that other teams can provision resources into. When one team is attempting to determine if stack drift has occurred, detecting deletions and modifications is relatively straightforward. In this case, the owner of the resource can call an API to describe the resource and compare it to the response of the expected response based on the infrastructure definition file. However, when multiple teams use the same bucket, this creates a more subtle problem because each team will also need to ensure that the new resources they detect don't belong to another team who is managing that resource in their own GitOps pipeline. There are a few tricks for accomplishing this, but we won't get into those today because they're usually very resource specific and they can be better addressed by more design consideration up front to reduce the amount of environment sharing that occurs. So if we set aside the multi-tenant issues and we look just at single-tenant architectures, there are a few ways that CloudFormation can help us. CloudFormation offers a feature called drift detection that can inspect your current template and the current resources that the template manages and tell you if drift has been detected. So let's look at an example of CloudFormation's drift detection. So what I have on the screen is the Bitbucket pipeline build configuration. In this first section, I added a script to detect drift. I do this by calling the CloudFormation detect stack drift API, and if I detect drift, I stop the build. So let's create some drift by going into the S3 console and making a change to the bucket I created earlier. I'm going to change the bucket versioning to suspend and then save the change. So if we look at the template file that's in source control, we can see that versioning is enabled. So the template does not match reality. So if I go into my Bitbucket Pipelines console and I rerun the last pipeline, I will eventually get an error. And if I look at the logs, I can see that my drift detection script detected drift and it stopped the build. Thank you for spending the last 20 or so minutes with me on this journey through GitOps. If you have any questions or feel like reaching out, I can be reached at my Twitter handle @CraigLefkowitz.